Through this course, heat exchanger design, let us further explain what a heat exchanger is. The course is split into 5 chapters. The first one is about how steam is used in various industries. Then comes the basics of steam in Chapter 2. Chapter 3 covers design concepts. And lastly, we have Chapters 4 and 5, which are all about the air-cooled heat exchanger and steam core air heater. These 2 types of heat exchangers are commonly found in our design codes. Chapter 1. Applications for steam in industry. Steam is used in many different industries, mainly for 2 purposes, as a power source and as a heat source. Regardless of how it's used, there are 2 common characteristics. Firstly, steam is usually produced and sent out at a positive pressure. In simple terms, it's supplied to equipment at pressures higher than 1 atm, equivalent to 1 atmospheric pressure, and temperatures above 100 degrees Celsius. Secondly, steam transfers heat to the product, raising its temperature. Afterward, it becomes a liquid called condensate. As a power source, steam is commonly used to drive things, such as in steam turbines. These turbines are crucial for generating electricity in thermoelectric power plants. After that, the steam coming out of the turbine at low pressure and low temperature gets completely condensed in an air-cooled heat exchanger, ACC or AC. The resulting condensed water, called condensate, is then recycled to the boiler and heated until it becomes saturated or superheated steam again. As a heat source, steam warms up the cold fluid by transferring its heat, and then it transforms into condensate, which is released through a steam trap. Chapter 2. Steam Theory. TH diagram. When water is heated, it gets hotter and eventually turns into steam. The properties of the steam can change depending on the pressure and temperature it experiences. The TH diagram shows what happens when water is heated under a constant pressure. From point 1 to point 2, we gradually heat the subcooled water until it starts boiling. Up to point 2, all the heat we add is used to make the water hotter. At this stage, the water is almost turning into steam, and we call it saturated water. This is called sensible heating. From point 2 to point 3, at the boiling point, which is the temperature corresponding to points 2 and 3, water begins to turn into vapor, and all the newly added heat is used for this change. During this time, the temperature doesn't rise anymore. It stays the same at the boiling point. We have both liquid water and steam present together. This is called latent heating. From point 3 to point 4. At point 3, all the water has turned into steam, and we call it dry saturated steam. When we add more heat to this dry steam, its temperature goes above the boiling point. The dry steam becomes superheated, and this is another form of sensible heating. In the TH diagram shown, we have the process of heating water under atmospheric pressure. The horizontal axis represents the amount of heat absorbed by a unit mass of water during the heating process, while the vertical axis shows the corresponding temperature change for the unit mass of water. Starting at point 1, where the water is at 0 degrees Celsius, we heat it continuously and its temperature can rise all the way to point 2, which is 100 degrees Celsius. This is the highest temperature at which water can exist as a liquid under this pressure. It is called boiling point. When we keep supplying heat, the liquid water gradually transforms into gaseous water vapor. However, the temperature of the water and water vapor mixture doesn't change. At this stage, the water is going through the phase change process. The wetness of water and water vapor decreases from 100% to 0%. Or we can say the dryness of the mixture, defined as the steam quality of the wet steam mixture, increases from 0% to 100%. At point 3, there is no liquid water content in the steam. Its steam quality is of 100%, and it has been fully transformed into dry saturated steam. When additional heat is applied above the boiling point temperature, it will, in turn, continue to increase the temperature of the steam. This dry steam is referred to as superheated. If comparing the heat absorbed by water in these two different heating processes, represented by the length along the horizontal axis, gray bar for sensible heating and red bar for latent heating, we can see the highest heat absorption occurs during the latent heating phase change process, known as the latent heat of vaporization for water. Steam tables are used as a reference source to calculate various properties of steam based on its temperature and pressure. You can quickly find a wide range of properties for both water and steam, such as specific volume, internal energy, enthalpy, entropy, and more. In the upper table, you will see data for superheated steam, where the steam is kept at a constant pressure, and its properties range from 200 degrees Celsius to 600 degrees Celsius. For example, water at a pressure of 10 bar absolute and a temperature of 300 degrees Celsius has an enthalpy of 3052 kilojoules per kilogram. The table below gives information about saturated water and steam. It shows that when the pressure in the water is higher, it requires more energy to make it stop boiling, which results in a higher boiling point. At a pressure of 9 bar absolute, its boiling point is 175.4 degrees Celsius. When the pressure increases to 12 bar absolute, its boiling point rises to 188 degrees Celsius. TLV International Incorporated is a Japanese company that provides products and services for steam systems. You can find helpful information about steam theory on their website. Chapter 3: Design Concepts. 1. Mass and heat balance. In a heat exchanger, where hot and cold fluids exchange heat, they must follow the principle of mass and heat balance. This implies that the mass flow rate of the working fluids remains constant. Moreover, the heat released by the hot fluid equals the heat absorbed by the cold fluid. For an air-cooled heat exchanger or a steam-cooled air heater, during the heat exchange process, the inner mass flow rate of steam and air is equal to their outlet mass flow rate, and the heat released by the steam equals the heat absorbed by the air. After releasing heat, the steam goes through a phase change and condenses into condensate. The picture shows 4 different ways that heat can be exchanged in an air-cooled heat exchanger or steam core air heater. The steam that goes into the heat exchanger is either superheated or in a saturated state. After the steam gives off heat to the air, it condenses into either subcooled water or saturated water. According to the principle of heat balance, the heat discharged by the steam equals the heat absorbed by the air, and this value can be determined using the following calculations. 1. The heat energy released by steam equals the product of its mass flow rate and the difference in enthalpy between its inlet and outlet. 2. The heat energy absorbed by air is equivalent to the mass flow rate of the air multiplied by its specific heat and the temperature difference between its inlet and outlet. 2. Heat exchanger sizing. When faced with the given thermal design conditions, the following sizing process is employed. Firstly, begin by selecting an appropriate tube arrangement and determining the heat transfer area it offers. Secondly, calculate both the overall heat transfer coefficient and the logarithmic mean temperature difference, abbreviated as LMTD. LMTD is a key factor, helps us understand the magnitude of the heat transfer driving force within the heat exchanger. Finally, repeat the above two steps until the provided equation matches up with an acceptable design allowance. Chapter 4. Air-cooled heat exchanger. Here, show 3 different devices set up in 2 cities in Taiwan, Keelung City and Kaohsiung City. The picture on the left is of an A-framed type air-cooled condenser. In the middle, you can see a horizontal forced draft air cooler. On the right, there is a horizontal induced draft air cooler. These air-cooled heat exchangers are used to cool fluids with ambient air. The advantages include no need to be located near a water source, easy getting air for cooling, and lower operational costs. However, there are also disadvantages, including lower thermal efficiency, the requirement for a large installation space, potential noise generation, and large effect on the operating performance for day-night and seasonal temperature variations. Next, let's introduce some terms and definitions related to air-cooled heat exchangers. Tube bundle, assembly of headers, tubes, and frames. Bay or module, one or more tube bundles serviced by 2 or more fans, including the structure, plenum, and other attendant equipment. It can be considered as the smallest and repeatable cooling unit, referred to as a bay for AC equipment and a module for ACC equipment, respectively. Item: one or more tube bundles for an individual service. Item number: purchaser's identification number for an item. Finned surface: total area of the outside surface on a finned tube exposed to air. Bare tube surface: total area of the outside surfaces of the tubes, based on the length measured between the outside faces of the header tube sheets. The image below shows typical bay and modular arrangements. AC equipment E121 has only one bay, and that bay is composed of 3 bundles. AC equipment E122 has 2 bays, and each bay is composed of 2 bundles. ACC equipment E221 has only one module, and that module is composed of 12 bundles. ACC equipment E222 has 3 modules, and each module is composed of 8 bundles. Horizontal type air-cooled heat exchanger mainly consists of 4 components: 2 bundles, transmission system, control system, and supporting structure. As for the A-framed type air-cooled condenser, in addition to those 4 main components, it also includes the following assembled parts: wind wall, A-framed sealing wall, exhaust duct, manifold steam duct, vacuum system, condensate tank, and A-framed structure. The diagram illustrates a typical bundle assembly for an air-cooled heat exchanger. Considering the inlet or outlet header faucets, there are 4 common styles: plug, cover plate, bonnet, and manifold. The transmission system is made up of 3 parts: a fan, a speed reducer, and a motor. Specifically, for the speed reducer, you can choose for either a gearbox or pulleys. Now, with regards to the control system, it may consist of 3 different control functions. Airflow adjustment. This is achieved through the use of louvers, variable frequency fan drive, and automatic variable pitch fan. Vibrations monitoring, utilizing vibration switches. Winterization. Special methods are employed to prevent water condensate from freezing inside tubes in cold climates. The following illustrates various types of air-cooled heat exchangers. Figure A depicts a single-phase vertical tube with forced draft. Figure B showcases a multi-phased vertical tube with induced draft. Figures C and D represent horizontal tube configurations with induced and forced draft, respectively. Figures E and F displayed inclined tube V-shaped designs with forced and induced draft, respectively. Figures G, H, and I exhibit heat exchangers with either horizontal or vertical tubes operating under natural draft conditions. API Standard 661 applies to horizontal type air-cooled heat exchangers, but can also be adapted for other configurations. It specifies design, material, fabrication, inspection, testing, and shipping requirements for such heat exchangers. Here are key design considerations covering the tube bundle, airside conditions, and structural aspects. A vacuum system is employed to maintain a vacuum within the air-cooled condenser. Its primary purposes are as follows. 1. During system startup, to create a negative pressure environment within the heat exchanger. 2. During normal operation, to discharge non-condensable gases which are mixed in the exhaust steam into the atmosphere. Besides, 2 commonly used vacuum systems are the liquid ring vacuum pump and the steam jet air ejector. Here is how the liquid ring vacuum pump functions. By rotating a multi-blade impeller located eccentricity within the cylindrical casing, the non-condensable gas is compressed and then released into the atmosphere. For a deeper understanding and a video demo, please visit the website. Additionally, the steam jet air ejector operates as follows. High-pressure motive steam enters the ejector through the inlet, creating a low-pressure area that draws in non-condensable gases from the air-cooled condenser. The mixture is discharged through a diffuser to the atmosphere. For more details and a video demonstration, visit these websites. Chapter 5. Steam coil air heater. A steam coil air heater is a type of heat exchanger by using steam to heat gaseous media such as air. On the left-hand side, the diagram shows a typical steam heater with vertical tubes. As steam transfers heat to the gas, it condenses into condensate, which is collected and then passes through a steam trap before going to a downstream storage tank. These types of steam coil air heaters are called different names depending on specific process requirements, like combustion air preheater, primary or secondary air heater, purge air heater, and white-plumed prevention air heater. Now, on the right-hand side, you will find two different designs. One includes a preheating section that uses hot condensate, initially depressurized to generate fresh steam to preheat incoming air. The other uses horizontal tubes to reheat flue gas, known as a gas reheater. A steam trap is a device used in steam systems to remove condensate and non-condensable gases such as air without letting live steam escape. It operates automatically and comes in various types, including ball-float steam traps, inverted bucket steam traps, biomagnetic steam traps, and thermodynamic steam traps. Among these options, the ball-float steam trap is the most common type in our applications. It offers several advantages for low-pressure systems. It ensures a continuous condensate discharge. It is suitable for handling large condensate loads and with a very low differential. It can operate effectively across a wide range of conditions. It has few moving parts, requiring less maintenance. Please visit the website for a demo video. Before discussing how to reduce vibration problem in steam coil air heaters, let's first explain the self-induced vibrations caused by common vortices. When a fluid flows around an obstacle, like a cylinder or sphere, it generates a low-pressure area behind it, known as a wake. As fluid speed increases, pairs of alternating vortices or common vortices formed within the wake. The images depict flow separation and water shedding behind a circular cylinder. A higher Reynolds number, R value, corresponds to greater fluid velocity. You can watch a demonstration video on this website. These vortices detach from the object and move downstream, generating a repetitive pattern at a particular frequency, referred to as the shedding frequency. Finally, the shedding vortices induce oscillating forces on the obstacle perpendicular to the flow, resulting in self-excited vibration. When water shedding frequency matches the tube bundle's natural frequency in a steam coil air heater, it causes resonance and vibration problem. To avoid this, make sure these frequencies are significantly different from each other in all oscillation modes. Natural frequency Fn depends on factors like tube length, weight, and how the tubes are supported. On the other hand, the water shedding frequency Fe relates to shear fluid velocity, tube diameter, and how the tubes are arranged. Ideally, these frequencies should differ by more than 20% to prevent resonance and tube vibrations. But if they are too close, adding bubbles can increase Fn, creating a greater separation from Fe in all modes, thus avoiding vibration problems. This course covers some compressed material that may take time for you to fully understand. In fact, the content serves as an introduction, providing a starting point for us to explore deeper together. Hopefully, you will find interesting topics as we go along.